So I'll say it again. In a few minutes, I'm going to ask you guys to show me a graph of a cart rolling down a ramp with the detector right there. And I would like you to tell me what the position graph looks like and what the velocity graph looks like. Now the truth is, I'm going to walk around the classroom, I'm going to look at your notes, and I want to see that you individually can do this. And anytime I hear you talking, I'm thinking that you individually can't do this. Not that I care if you're silent or not, but how do I know if you can do it if it requires conversation with the person around you? So you either can or you can't. And you've got 30 more seconds to prove which one you can, which one of you can. I'm just going to ask questions. And I don't expect you to answer them. I expect you to look at your paper and evaluate what you did. At time 0, the cart will be next to the sensor. And that's when I'm going to let go of the car. So, where's the car at time 0? I don't want an answer. What your graph should look like. How fast is it moving at time 0? How does the slope of the velocity graph look at time 0? How does the slope of the position graph look at time 0? Does your graph on the left agree with your graph on the right? Because they're related. After some period of time, the car will have moved away from the detector and will be located where it is now, at the bottom of the track. When it gets there, is it still moving? When it gets there, is it in the positive direction away from the detector or the negative direction away from the detector? When it gets there, what should the slope of that graph look like? The velocity graph. Does it show positive velocity or negative velocity? What does the slope of that graph look like? Does your graph corroborate? Does the left side of the graph agree with the right side of the graph? Now, having said all of those things, let's check your work. At time 0, the car is at rest. Now, here's where you're probably going to get something wrong. I'm not going to punish you for it. It's not at 0 in the position graph. The meter can't see 0. It might be at like 20 centimeters, but it can't see 0. I'd forgive you for that one, though. So don't run away erasing it. If this were on a test, that'd be just fine. Now, how do I make sure these two things agree? Well, one way to make them agree is to realize that the velocity graph is the slope of the position graph. You have to really keep this in mind. That is the most important thing I can say today. And if you're not thinking about it, you are going to be unsuccessful the next week. The velocity graph is the slope of the position graph, which means that the slope of the position graph has to reflect the fact that the velocity is 0. The slope of the position graph must also be 0. So I put a little line in there to remind me that the slope there is flat. Now, this next one we haven't talked about, but you should know. The slope of the velocity graph should be positive. The car's velocity is going to become more positive. It's moving away from the detector, which means the position is changing in a positive way away from the detector. So the velocity is becoming more positive. So I should have a slope that is positive on the velocity graph. We should also know that the slope of the velocity graph is the acceleration. So if we know the acceleration, we know the slope of the velocity graph. In the same way as if we know the velocity, we know the slope of the position graph. This is a critical understanding. Now, This part is not a surprise. After a few moments' time, we know that the car's velocity has increased to some positive number. The track is the same inclination the whole time. Having practiced this yesterday, it should be clear that a straight line connects these. More importantly, it should be pretty clear that the velocity here is the same, the slope here of the velocity graph is the same as it was at the beginning. It should be a straight line. All of these slopes should be the same. Because in this case, the acceleration was constant. On the other hand, although the object got further away from the origin, which means its position got over here someplace, the slopes for the position graph should not all be the same, because the slopes of the position graphs are the velocity. By the end, it has some positive velocity, which means that at the end, the slope of the position graph should be some positive number. That suggests that the position graph looked like this. Now, I want to be kind of direct with you here. Some of you didn't have this correct. I would encourage you not to jump at answers or guess at them. I am confident that if you reason out what it should look like by asking yourself questions about the starting place and the ending place, you will do a better job of getting this right. Because I know on your first test, which is likely next week, Wednesday or Thursday, one of your multiple choice questions, which you'll have to answer in 1 minute and 12 seconds, is going to have a situation and is going to have 5 different potential graph options, and you'll have to choose them. Probably the same set of graphs used for questions about position and velocity with just no markers on them. You'll need to be coming to grips that recognition is important, but reasoning it out will always save the day. Now, we're going to go one step further now. Since we've got all this stuff set up, and I've tried to kind of make this something we can use for laboratory time too, I want to see if we can't come up with a set of data that matches this all out. So we're going to start a new experiment. Table 6, file, new, discard, join new experiment. There we go. I'm going to set a 3-second experiment, because that seemed to work okay. And we're going to go 50 samples per second. And let's see, I'm just going to burn off a set of data real quick while I get this set up. And here we go. We're going to take a real set of data this time. Ready, set, and release. Oh, not great, Mr. Sheldon. Close. Ready, set, and release. That was better. All right, so all the features I want to see in the graph. Velocity graph showing a nice positive slope, starting from nearly rest. Position graph clearly starting not at 0. I hope you guys can see that. This graph seems to start somewhere around 0.2. Not a surprise, can't see inside there, so there's no point in seeing that. On your lab, you're supposed to create a model for each one. Let's see what I'm going to expect of that model. So I'm going to tell you the numbers I see here. Can you write the mathematical model that goes with your velocity graph? Based on this set of data, the value for m, 0.314. The value for b, 0.06696. I'll state it again. Although if you're desperate to read it with your own eyes because you don't trust me, fine. But the numbers are small and I'm not going to make any reasonable attempt to make them bigger. Slope, 0.314. Y-intercept, 0.06696. Now what I'm expecting to see is you understand that this is the velocity versus time graph. So as a model goes, v is a function of t. Should have 0.314 t plus 0.06696. That's our model. Now, your position model is a little different because we have a function for position already that we are using. That function of position is on the board behind me. Making it a function equation means I separate out the delta x, and I write this as 1/2 a t squared plus v naught times t plus x naught. I'm leaving some space in here because I haven't actually gone over here and looked at what the potential curve fit is. So let's find the curve fit here. Apply my curve fit. Choose quadratic, because that seems like the one that it looks like. I get, for A, 0.1576. For B, 0.06838. And for C, 0.17. That's got to be the initial position. It's located about 17 centimeters away from the detector. Not a surprise. I expect that. B was 0.6838. Guess he's had enough. Now, parentheses. We know that in this formula there's a 1/2 out there. I want to drive this point home. The value for A is 0.1576. So I'm going to double that. Put it inside the parentheses, which is going to give me, what, 0.3152. Now, there's reasons why I want you to do this. First, I want to emphasize the initial position is available to us in the position function, but not available to us in the velocity function. No place for it there. But the initial velocity, oh, it's 0.068. I forgot the 0.0. I'm going to have to squeeze it in there, folks. Be kind to my handwriting here. Plus 0.06838. Still, 0.06838, 0.06696. Those are close. Real close. They're not rest, though, which means that it was clearly moving when the detector started. Very little I can do about that. Acceleration, 0.314, 0.315. Nice and close. But here's the thing I want you to take home with you, the thing I really want you to dive into. This function is an expression of all of the slopes of this function. It has to be. If the slope of the position graph is velocity, and I have an equation of velocity, then I have an equation that is the slopes of the position graph. Now, if you don't understand that, or you're having a hard time wrapping your mind around that, then imagine this homework assignment. I produced for you a graph on graph paper, a nice big one, of the position graph, the one on the left. I give you this function, but ask for you to tell me the slope right here at 1.6 seconds. If all you have is the graph, even with the function, your current set of skills might limit your options. One way of doing it, and trust me, I have several assignments I could assign to have you do this, is to plot a tangent line. Right, a tangent line touches the curve at only one point. And then from the tangent line, do rise over run to get the slope. That would tell me the velocity at the 1.6 second mark. This is how algebra solves this problem. But algebra has also given you more. It's given you insight. Algebra produced for us this function. Right? We got that from just looking at the slope of a velocity graph. That's where we got that function from. And using more algebra, area of the curve, and doing some substitution, we got this function, where the object is. Now, there's a relationship between these two functions. This is something that Newton saw. And Newton created a form of mathematics that could produce the velocity function from the position function and vice versa, without having to graph it. That's all calculus really does. Now, I want you to understand that we're going to learn what this is. I'm going to teach it to you. It's not particularly hard to learn, but I'm doing it without teaching you the fundamental theorem of calculus. I'm just going to show you the rules. Does everybody understand this? I'll show you the rules. Unfortunately, there's symbology that goes with this that's going to be lost on you. But I think that'll be okay. I'm willing to sacrifice some symbols in favor of you just getting an appreciation for how these things are related. What you might not know, and this is for all the people in the room, not just people who think they're calculus experts, is that calculus is a form of algebra. Calculus is called the algebra of functions. It's called that because of what it does. Algebra allows you to see the relationship between all numbers, not the relationship between specific numbers, but all numbers. That's what I have here. I have x as a function of t. I have related together every possible time and a position to go with it. That's what algebra does. It relates together numbers, even numbers that we don't know are related. Calculus does the same thing for functions. It shows you how one equation is functionally related to another equation. That's what calculus is about. It's just another form of algebra. So when we look at calculus, there's no mystery here. Calculus is going to be all about finding functions. I give you one function, like velocity or acceleration or position. You produce another function. It has other uses too. Like any tool, there's multiple uses for a lot of tools. But that's what it is. It is a tool. Now, to fully appreciate this, I do want you to understand that the position graph has something that would be related to slope. We called it velocity, but remember, in the old days, slope was rise over run. So for a simple position graph, if I wanted to find the slope, your method for finding slope in the old days was to choose 2 points and find delta x over delta t. That would be the slope. And we've gone one step further. We've defined velocity by the slope of position. We've made a definition. The problem here is that the delta suggests we can choose 2 points and find the slope between those 2 points. we have come to the realization that because it's curved, that's not really going to be the slope. So the first thing that we're going to do is we're going to change the symbols to recognize that we're looking at a slope at a specific point in time. So instead of a delta, which looks at a change over several pieces of data, we're going to reduce it down to saying this process produces the slope at a single point in time. Now, calculus will allow you to spend a month or two talking about dividing by zero. It's all fun. Ask anybody who's had calculus. They love those limit formulas. You guys are in pre-calc now and doing all those function things with the weird lines that stop and then start someplace else. That's all you're doing in pre-calc right now, and it's boring because you did it in Algebra 2. All the people in calculus at the beginning of the year had to do a bunch of pages full of limits to prepare them to do their calculus stuff. So they did all the review stuff too. It's all in anticipation of doing just this thing. Now, I'm going to change this a little bit, but I want you to understand that the thing on the right says, if you want to translate this, the derivative of x with respect to the variable t, or respect to the function of t. That's how I would translate this. In fact, you'll see me write this sometimes as this. They are functionally identical. I've just factored out this portion, which I want you to treat like an operation. You're going to perform something on your function. It's still just finding the slopes. It's just a different way of doing so. Now, I'm saying those things to you, but I don't want you to get too locked into this. If I have z equals dw to the fourth, right now, you don't know what the functional variable is. I could tell you that z is a function of d, which means w to the fourth, is the constant, and d is the variable that's changing all the time. Or I could tell you that z is a function of w, which means d is the constant, and w is the part that's changing all the time. Ours are specific. We have x as a function of t. That's specific. We have all sorts of other letters in here, but we're suspecting that these letters represent things that aren't changing, and the t is the function. The reason this is important is when I say dx dt, I'm telling you t is the important variable. Everything else is just a number that doesn't change. But t is the important variable. You focus on t. Good so far? So, we're going to do the derivative stuff tomorrow because the bell's going to ring in a minute? But I want you to walk away with this. Don't pack up yet. I just want to make sure you understand that we're going to close right now. This phrasing means to take a function with respect to t and apply That's what this means. So when I say those things tomorrow, I'm saying you must go find a function that has x and t in it. And we're applying the derivative with respect to t. That's what this symbology means. the result will be an equation for velocity as a function of t. That's what the result will be. When we do this, we get a new equation that's going to be a function with respect to t. The only reason I won't explain it now is because I won't finish, and that'll bug me. So now you can tack up your stuff.